It's about the use of ray tracing programmable frameworks for radio wave propagation prediction. And we have done this on the Universidad de Alcalá de Henares. So what we're going to be discussing here, well, we have a brief introduction about what we are doing. We'll discuss what is ray tracing, what is wave propagation calculation, and the different models that we can use. A proposed input for our problem, ray tracing frameworks with NVIDIA optics and plot optics framework, and a proposed ray tracing algorithm to calculate the wave propagation. So first things first, we propose to use ray tracing techniques to model wave propagation. The idea that we have is to calculate the possible paths between the emitter and the receiver through a 3D environment using a deterministic model. Once we have all the possible paths, Maxwell's equations can be applied to calculate the path loss and receive power. So we are going to be shooting rays, see where they hit and where they don't hit, and we are going to apply a mathematical model to model the radio path loss and receive power. So what is ray tracing? Well, very briefly, the ray tracing technique is the idea of shooting rays from an origin point, usually the camera or an eye, to a scene composed by different objects and get information about where the rays are hitting and reflecting. So what we need to calculate is the number of ray pulses and its coordinates where they're hitting, the ray hits or misses on different objects and surface, and the distance travels by this shooting rays. This will be needed to modulate the wave propagation and the loss. So we have two kind of models to get the radio wave propagation. We will have empirical models that are simple mathematical formulations expressing the impact of encountering obstacles on the radio wave during its propagations. The proposed formulations are simple and easy to use, but lack the accuracy. And we have deterministic models that simulate radio wave propagations. They take into account the environment and the interaction between the waves and the obstacles, resulting in more complex algorithms that take more resources. So we will have, to put it briefly, empirical models that are not that accurate, but are pretty fast. And we have deterministic models that are very more accurate, but they are more slow and take more resources. So for the simple deterministic ray tracing input, for our use case, we will be needed a 3D environment that represents a street, another environment, a city, whatever 3D scenario you want. A emitter, which will be one point on a 3D environment that shoots rays in any direction. And the receiver, that will be a simple SSR with an appropriate radius. It is important to denote that if the radius is too small, maybe it won't be hit by any ray. And if the radius is too big, maybe it will be hit by multiple similar rays. So all the duplicate rays must be removed before applying electromagnetic equations. You can see on this image example that we are having a sphere which is too big, and thus there are similar rays exactly for on this image that are hitting, that will be the same ray, but since the sphere is too big, it's getting a lot of rays. So we will have to combine these 4 rays into one. We have a lot of frameworks that works for ray tracing, but we find NVIDIA optics as the most suitable option for multiple reasons. The first one will be that it takes advantages of NVIDIA CUDA graphic cards, resulting in optimal and scalable performance. It's flexible enough to allow us to collect and send the custom data related to the rays between the transmitter and the receiver, the hits, the distance traveled, etc. And it allows to take advantage of CUDA parallelization capabilities when running the radio propagation prediction algorithms. So apart from using it to simulate the rays, we can take advantage of the parallelization software that it includes. So optics is a very large framework, and it's difficult to learn and to use. And you have to know a lot of little details about how it's precisely working. So we propose to use plot optics framework, which is a Python package that works as an interface for NVIDIA optics, focusing on image data representation. It allows us combining components prototyped in the high-level language, which is Python, but with the optimized workflow of the underlying optics ray tracing engine. So we will be writing very simple code on Python that it transforms in very optimized but difficult code on optics. It allows us to load an OBJ waveform 3D file, which will be the city or the street where we want to run the simulation. and situate different geometries on the scene. The proposed algorithm is based on the use of this tool. So what are the prerequisites of the proposed algorithm? Well, it will be that the input must match the following prerequisites: that all the 3D faces on our OBJ 3D object will be triangles. It has to be triangulated, which is the process of dividing a polygon into multiple triangles, as you can see on the bottom right image. So there's that, it must be triangulated. A thin small cylinder segment must be added on building corners in order to implement diffraction. This is for the way that optics works. It has to reflect the rays with a cylinder on the corners. And the 3D faces must have a normal vector, since it is used for the reflection. The normal vector will be a vector that is perpendicular to the face surface, as you can see on the image. And so that we have our prerequisites and we have all the things that we need to run the algorithm, the proposed algorithm will be as it follows. First, we will start with a relative dense distribution of rays starting from measurable point. This will be the camera side or the emitter. We will save the output on the output, the heat position, the object ID, and normal information of the rays. We will split the reflection heat on faces and the fractional heat on edges. It is easy to know if the face is a wireframe segment, an edge, or have been hit, and at which angle. So we have all the information that we need to use the Maxwell equations. Then we will continue shooting reflecting rays. Each time we are saving edge hits for later, and we will repeat that until some max reflection, so we can define how many reflections do we want to make a direct rate, a 2 reflected ray, a 3 times reflected rate, etc. So at this point, multi-reflection cases are completed. Hopefully some ended at the transmitter, and there must be a buffer of primary, secondary, and so on edge hits, hopefully not enormous. And now edge hits from the buffer are processed in batches. So the first thing we do is calculate the directions of number of outgoing segments for each edge hit. This will cover a cone with a constant beta angle and a range of phi. That will be the Keller's cone. And then we follow the rays like we did before, continue with shooting reflected rays, maybe with a lower number of segments. We will continue this until the buffer of edge hits is empty and we have all the rays, hits, and distance stored. Then we can apply the Maxwell equations and compute the data loss of receive power. So the conclusion will be that it is expected that the ray tracing algorithm that I just comment will be applicable and writable on plot optics and the premises described. It is expected that the parallelization techniques on GPUs will permit a real-time simulations for future wireless systems and provide better performance than other solutions. And the approach described should provide multidimensional coverage maps in 3D for both indoor and outdoor environments, or any 3D environment, really. And that will be the end of my presentations. Thank you so much. And do you have any questions?
Thank you, Macros, for your wonderful.